Tēnā koutou. My name is Loretta Garrett from Scion, and today I'm presenting on the Puruki Experimental Forest. The outline of the talk will step through some history of Puruki, the legacy Puruki has made, some key findings, and what are the next steps for Puruki. Puruki Experimental Basin is located in the central North Island, just south of Rotorua, and is made up of 3 different land uses, of which Puruki is one. Puruki Experimental Basin was established in 1968 under the umbrella of the International Hydrological Decade, a partnership of 3 government departments: Lands and Survey, the former site owner, the Ministry of Works, Water and Soil Division, and the Forest Research Institute of New Zealand, now Scion, designed and implemented an ambitious program of long-term research to understand the effects of land use change on the hydrological regime. In addition to hydrological research, the Forest Research Institute instigated research aligned with the International Biological Program, focused on productivity and dry matter production in planted forests. The installation of the paired catchment site was visionary in ambition and scope, interagencies, and has longitudinal data sets with value that have compounded over time. By the close of 1968, 59 catchments were installed across New Zealand as part of this representative program. Today, only Puruki is still actively monitored, making the site unique and a very special resource. Puruki Experimental Forest is part of the Puruki Experimental Basin. Puruki and the surrounding catchments were converted from native forest to pasture in the 1920s. Over time, the land was neglected and colonised by manuka scrub and second growth hardwood. In 1957, the land was cleared once again and restored to pasture for sheep and beef farming. Then in 1973, Puruki was planted in Pinus radiata for the first time. It has remained under pine forest to this day. The land is currently owned by Landcorp, Pamu, and Scion has a lease agreement to continue operating at Puruki as a research forest into the next rotation. Puruki Experimental Forest was established in response to a call by international organisations to establish long-term trials to monitor the impacts of change. Over half a century later, we need to monitor change and adapt to its challenges have never been greater. Over the decades, Puruki has supported numerous research areas well beyond the original objectives of the site. The legacy of Puruki includes greater understanding of the impact of land use on water yield and quality and soil carbon and nutrients. Within Puruki, we have improved knowledge on forest health, nutrition and disease, growth by genetics, by environment, by nutrition, growth by solar radiation, and the use of LiDAR for remote monitoring. Data from Puruki has been invaluable in the development and parameterisation of New Zealand's forest carbon, nutritional and forest productive models. For example, scene change, the forest carbon predictor, and the nutrient balance model, NewBAM. All of these models are highly significant tools for planted forest management and reporting. It has provided new knowledge on needle disease, nutrient limitations to growth, pine genetics by environment interactions, and data for hydrological modelling and water quality. All of this has been made possible by the infrastructure of the Puruki forest and the drive to keep the experimental forest active. One key infrastructure is the Met Tower, which was active during the first rotation with a CR7 logger system. This climate data has supported all research undertaken at the catchment. The Puruki water weir, located at the base of the catchment, has been a key infrastructure for Puruki, and in the first rotation, the paired land use comparisons allowed for questions around water quality and quantity to be addressed. This is one of the major outcomes from this paired experimental basin. The work showed how over a growing rotation, the annual water yield in the stream decreases compared to pasture land use. It also demonstrated that planted forests have the potential to supply water to downstream users during dry spring and summer months when compared to pasture land use. Plus, it is able to regulate storm flow in wet winter months compared to pasture, resulting in reduced peak flows and small floods as much as by 50%. Within Puruki, upper mid-crown yellowing, a magnesium-potassium nutrient deficiency was observed and research was targeted towards tree nutrition. The findings were planting stock showed a large and heritable variation in upper mid-crown yellowing occurrence, and within site soil variation contributed towards the upper mid-crown yellowing occurrence. Detailed measurements were made to inform wider catchment hydrology, such as stem water flow, and to understand the dynamics of root decay and nutrient cycling. Over time, multiple tree biomasses have occurred, of which the data has underpinned the forest carbon predictor and the nutrient balance model. And deep soil sampling has informed on how much soil carbon the site has and supported the impact of harvesting method on soil carbon stocks, with results showing Puruki has a high amount of soil carbon, about 145 megagrams per hectare of carbon in the top 1 metre of soil depth. The experimental trial infrastructure currently at Puruki is made up of 3 key trials: phenotypic selection by upper mid-crown yellow tolerance, genetics by environment for upper mid-crown yellowing, and seed lot comparison in relation to solar radiation. These experimental plots were established using a range of genotypes from unimproved GF2 stock from Riverhead Forest, 400 genotypes made up of Puruki and Nelson clones of contrasting nutritional characteristics, a Puruki control seed lot made from GF7 stock from the first rotation at Puruki, selected specifically for tree health, and 2 commercially available genotypes, GF30 and a high density stock. Another legacy of Puruki is the installation of a national trial series at 14 sites, which is made up of clonal material planted at the second rotation Puruki forest. I'll now step through some key findings from Puruki, specifically focused on improving forest productivity and managing nutrients for productivity and water quality. This figure shows the productivity of Puruki's first rotation. The stock was GF7 planted at 2,200 stems per hectare, with a number of different thinning rates from unthinned to 550 down to 60 stems per hectare at end of rotation. We now overlay the second rotation productivity for selected planting stock and compare it to the first. Improved clonal stock of GF30 in the high density breed and the Puruki control GF7 seed lot all show improved productivity. We can see that for all improved genotypes such as the GF30, the productivity has been greatly increased. This table gives you some numbers. on the first and second rotation productivity between planting stock at age 20 years. With improved genotypes and higher stocking rates, Puruki had a 54% increase in productivity in the second rotation when compared to the first. This increase has come about through selecting superior genotypes and planting at high stocking on a high fertile site affected by nutritional problems and disease problems. The next two slides demonstrate that we can have high productivity with low impacts on water quality. This slide shows a nutrient balance model output of tree biomass and forest floor stocks over 2 rotations. The first rotation accumulated 1,011 kilograms of nitrogen per hectare at the end of rotation in the live biomass pools and the forest floor. This nitrogen was sourced entirely from the soil. In the second rotation, half the site was planted at 500 stems per hectare with no thinning. This management held a similar amount of nitrogen on site in that biomass pool. With the improved Puruki clone stock selected for tree health, the nitrogen accumulation increases by an additional 340 kilograms of nitrogen per hectare. And with planting a GF30 stock, a further 534 kilograms of nitrogen per hectare is accumulated in that second rotation. And this is what we saw reflected in that growth data as well. This demonstrates that with improved genotypes and higher growth, the demand for nutrients from the site will also be higher. This slide shows the nitrogen loss in kilograms per hectare per year over the first rotation and part way into the second. If we take the average nitrate loss across the first rotation, the value is less than 2 kilograms of nitrogen per hectare per year being lost to the stream. This research offers the potential to develop persistent, high productivity, high nitrogen forest management systems that have negligible impacts on water quality. The water quality measurements have been reactivated and are starting to now monitor going into the end of the second rotation. The next steps for Puruki are to collect valuable end of rotation data on productivity, wood quality and water quality. And with coming to harvest age for Puruki, we are now thinking about what the third rotation will look like. We are keen to maintain the visionary approach from 1968 with multi-agency collaboration, long-term forest research trials of international importance, and extend and challenge the boundaries of existing planted forest trials. The results will be the potential for transformative outcomes for forest management. Ngā mihi.